Hello everyone. This is a continuation of the equivalence proof that we started in a previous video. If you haven't viewed that video yet, you should go back and find it before proceeding. So in this video, we're going to do the second derivation. We're going to prove that the existential generalization, there's an x, there's a y, if px then qy, is derivable from the conditional. If for all x px, then there is a y qy. Let's go ahead and get started. So we're deriving the existential. There's an x, there's a y, if px, then qy. We're going to derive that from if for all x px, then there is a y qy. That's our primary assumption. It's going to be kind of a long proof. So that's a hint. Okay, and we're going to put our target sentence down here at the bottom. There's an x, there's a y, if px, then qy. Okay, this would be a good time to hit pause and come up with an idea about how to strategize. When you're ready, resume the video. Okay, so there's a number of ways of going about this derivation. In fact, there's a number of ways of going about every derivation. I think the best way to do this one is indirectly by negation elimination. What that means is that up on line 2, we're actually going to start a subderivation and assume the opposite, the denial, of what we want. So there's an x. Tilde, there's an x. There's a y. Px, horseshoe, qy. That'll be an assumption for negation elimination. Okay, so you may have come up with a different strategy when I asked you to pause the video and think up one. And so what I want to ask you to do is maybe set that aside and proceed with this, this strategy. So copy down a derivation that has this subderivation, because this is the one we're going to work out in this video. So I'll give you a moment. If you need to take a moment, hit pause, and then when you are ready to go, you can resume the video. Okay, so remember, in an indirect proof, negation introduction or negation elimination, we don't have a clear predetermined target. The rule statement doesn't give us very much guidance. What the rule statement says is that we have to have any sentence of the language and its explicit denial along the scope line of this subderivation. Okay, so we're going to have to just feel our way around for a while. That's actually not a bad strategy. So what we're going to do in this proof is just start applying the rules that we see an opportunity to apply. Let's look at line 1. It's a conditional. We know that conditionals don't play well by themselves. They always have to have some other statement to interact with. If you're thinking conditional elimination or modus tollens, you know that you need to have something other than the conditional. Those rules take 2 line numbers as input. But when we look at line 2, we have the negation sign in front of an existential generalization. That's actually kind of nice because existentials are no fun to work with. Nobody likes using existential elimination. But when we see a negation sign in front of an existential, that's input for quantifier negation. So we're going to drag the negation sign across that first quantifier and turn the quantifier from existential to universal. And we don't change anything else about that sentence. So that's line 2, quantifier negation. Okay? And again, it doesn't matter too much for the order in which you apply these rules, but here again we see a negation sign to the left of an existential quantifier. So we have input once again for quantifier negation. This time we get for all x, for all y, tilde, px, horseshoe, qy. Okay? So that's line 3, quantifier negation. We have now then, right, 2 universal quantifiers stacked right next to one another. So one thing we can do is start eliminating those universal quantifiers. We can start instantiating these universal generalizations one at a time, starting with the main operator for all x. So we're going to drop that quantifier for all x. We're going to come over here and replace the variable of quantification with a name. Universal elimination has no restrictions on names. We'll just choose the name A. For all y, tilde, PA, horseshoe, QY. That's from line 4, universal elimination. Then we're going to drop this y quantifier and replace the y variable with some name. We could choose any name we want. And even thinking downstream, we could choose a different name here. But I'm going to go ahead and stick with A. PA, horseshoe, QA. It'll all work out if you choose a different name there, but I'm keeping A. So 2 applications of quantifier negation followed by 2 applications of universal elimination give us this much simpler sentence to work with. And then, of course, we still have line 1 up here we haven't touched. Let's keep it in mind. Now might be a good time for you to hit pause and see if you can work out some next steps. Remember, all we're looking for is a sentence of the language and its explicit negation. Go ahead and hit pause, and when you're ready, when you have a few steps, hit resume. The next few steps, we're going to go ahead and stick with what we're working on. The next few steps are steps we've seen back in predicate derivations. The first step I'm going to do is apply implication to line 6. That's 6 implication. And of course, I've only applied it to the expression that's between the parentheses. I leave the tilde and the parentheses the way they are, and I only applied implication to this section in the middle, okay? Now this looks like input for De Morgan's, and it is. So let's go ahead and apply De Morgan's. Tilde, tilde, PA, ampersand, tilde, QA. That's line 7, De Morgan's. Line 9, we might just want to drop those 2 tildes there. PA, ampersand, tilde, QA. That's line 8, double negation. If I take PA off of there by conjunction elimination, I have a sentence that I can do universal introduction on. For all x, px. That's line 10, universal introduction. I just want to make clear we've taken this a, replace it with an x, and put the universal quantifier on. We can only do that if the name A does not appear in any live assumptions. So we go back up here to our 2 live assumptions, and the name A doesn't appear. In fact, the name A was introduced by the rule universal elimination. So that's a good indicator that we can probably do universal introduction on that name. The result is that it gives us something to work with our conditional with. So we have if for all x, px, then there's a y cubed y. And then down here on line 11, we have for all x, px. So that gives us, there's a y q y. That's from 1 and 11 conditional elimination. Okay? So I'm anticipating a need for more room here. We're going to have to create a bit more space. That's okay. So line 13, what could we do with line 13? Well, we've broken this conjunction in two. We've broken it, the left side, use universal introduction. That allowed us to use conditional elimination. Let's come back to the right side of the conjunction, not QA. From line 9, conjunction elimination. Why don't you hit pause here and see if you can make anything out of that, not QA. And if you come up with some ideas, then you can resume the video and see how things turn out. Well, like PA, the statement tilde QA is also input for universal introduction. I'm going to use the y variable here, and I think you're going to be able to see why. So line 13 line 14 is universal introduction on line 13. We have for all y tilde qy. If we drag the negation sign across the quantifier, by quantifier negation, that gives us what? Well, it gives us this sentence there. It's not the case that there's a yqy. Look at line 12. If line 12 is our q, line 15 is our not q. I'm going to try to draw as straight a line here as I can. There we go. We have a sentence and its negation. We have a sentence and its negation along our subderivations scope line. What that means is that we can come to the next outer scope line and write down the negate from line 2. So line 2 was the negation of our target sentence. We have a sentence and its negation along the scope line of that assumption. And so negation elimination tells us, well, we can just take the negation sign off and write that down along the next outer scope line, in this case, the main scope line. And then that concludes our proof.